Welcome back. In the last few videos, we've been looking at how to use E-cell values to say whether or not a reaction is feasible or not. We've also looked at the limiting factors that might turn a reaction from non-feasible to feasible by changing the standard conditions, or where the reaction may appear not to be working because the activation is too high, so the reaction is not observed under normal conditions. A lot of these concepts you've come across before in both equilibria and, more importantly, in entropy, and it therefore shouldn't be surprising that E-cells, entropy and equilibria are all linked. And we're going to look at that on page 15 of your notes. So as you'd expect, E-cell and entropy are linked because they both tell us something about the position of equilibrium. So we know from our equilibria notes that delta S total equals R ln K. That's the equilibrium constant. We know from our entropy notes as well that delta G is equal to minus RT ln K. As we expect, the E-cell values are strongly linked to entropy because they're all measuring the same thing, and they're related via what we call the Nernst equation. T delta S total is equal to NFE cell, where N is the number of electrons transferred. And that is why when we work out E-cell values, we don't times up no matter how many electrons are being transferred. That's because they're accounted for here instead. You don't need to learn any of these equations, but you do need to be able to use the Nernst equation, and you need to be able to understand how these things are related. So how E-cell, Gibbs, entropy and K values are all interrelated. Putting the two equations together, we get this E-cell value. So E-cell is equal to RT divided by NF, and those are all constants, times the ln of the K value. The thing you do have to know is how E-cell varies with delta S total and how E-cell varies with ln K. And in both cases, they are directly proportional. So E-cell is directly proportional to delta S total, and E-cell is also directly proportional to ln K. So as delta S total increases, E-cell will increase. As ln K increases, so will E-cell. Now we can put these together to work out, for example, here, if I've got a zinc copper battery and I've been given the voltage, so I've been given the E-cell value, and I can work out what the total entropy change for the reaction is. Given the equation, all I need to do is plug in the numbers. And if I work this out, it comes out to plus 712 joules per mole per Kelvin. And as you'd expect, as this reaction is feasible, it's got a positive sign here. So moving across to page 16, and on page 16 there is a table. The table that links delta G, delta S total, E-cell and equilibrium constant Kc. And it's probably one of the most important pages you're going to ever find in your A-level course, because it answers one very basic question, a question which we've been asking since the beginning of the course. Why does a chemical reaction happen? What is it that prioritizes the products over the reactants? And the answers are on this page. It comes back ultimately to this value here, the delta S total value, but it's linked to the other three as well. Fix any one of these values and all the others are fixed. What this basically means that delta S total, if we know that the delta S total value is positive, we therefore know something about delta G, we know something about E-cell, and we know something about our equilibrium constant Kc. If this is a positive value, no matter what value it is, we know that delta G will be negative, we know that the E-cell will be positive, and we know that Kc will be greater than 1. Likewise, we know that if delta S total is negative, delta G will be positive, E-cell will be negative, and our Kc value will lie somewhere between 0 and 1. Any one of these numbers fixes the other three. So if we work out that the E cell is positive, delta G must be negative, delta S total must be positive, and our Kc, or equilibrium value, must be above 1. All four talk about the same thing, the position of equilibria. So a very negative delta G, positive delta S total, a positive E cell, and a K value greater than 10 to the 10. Basically, we don't bother with a reversible sign for these because they pretty much go to completion. In this second row, again, delta G is still negative, delta S total is still positive, and so on. So we would still say that this reaction was feasible. It's probably a little bit of a reversible reaction, but we certainly get more products than reactants. So we would say that the position of equilibria lies over towards the reactants. On the other end of the scale, if you've got a delta G value of more than plus 60 or a delta S total less than minus 200, we don't bother with any sign for this one. We just say there is no reaction here. These two are not going to react together. Likewise, if we've got smaller values, plus 10, greater than minus 40 or less than minus 40, and so on, then again we would put an equilibrium sign on those type of reactions, but again we would say the equilibrium position lies over towards the reactants. This would be a non-feasible reaction. Remember, as a chemist, we define feasibility as a reaction where the delta S total is greater than 0. That is what we define as feasible. Obviously, the bigger that value, the more over to the side of the products the equilibrium position lies. If you like, the more feasible that reaction is. But even a small positive there, we would say it's feasible because we have, on ratio, more products than we have reactants. And that finishes this section of the notes with this very important idea that these 4 principles that you've studied over the course of nearly 2 years are all interrelated. They are all connected because they all give us some information about the position of equilibria, and they tell us that answer to that very fundamental question: is the reaction going to happen?